Hi, and welcome to another lecture of the video lecture series of Fundamentals of Machine Design. In this particular lecture, we will see the relationship between the stress and strain and try to plot a diagram between them so that we can identify the diagrams for different materials. This will help you to define the material for a particular working condition. And that's why this is very important topic based on which many definitions have been made and many parameters have been discussed. So this will help you to understand those parameters and definition in the further upcoming lectures. So first of all, we will take an example of a steel material as a specimen on which we will be discussing our scenario. So first of all, take a specimen of a steel material. And on this specimen, we will apply a force or an external tensile force of equal magnitude in an opposite direction. So this whole application is generated in a UTM or a universal testing machine, in which we gradually increase the tensile force so that we can get the different variation in the strain, and according to that strain, we will get the different values of the strain as a readings. Okay, so first of all, the steel specimen is loaded in the UTM, that is the universal testing machine, in which tensile forces will be applied and the value of these tensile forces will be gradually increased. So this is our diagram in which the steel material is shown. On that particular material, the tensile forces are shown in the opposite direction and the value of these forces is P. As soon as you increase the value of this force P, the material will try to elongate, and due to this elongation, the strain value of the material will also increase. So as you can see, our diagram, we will try to plot a diagram between the stress and strain parameters, and for that particular diagram, the strain will be the main parameter based on which the stress will be the dependent variable, or we can say that the strain will be the independent variable and stress will be the dependent variable. And that's why we have represented the strain on the horizontal axis, and with changing the value of the strain, we will get the different readings of the strain on the vertical y-axis. Now, first of all, when you increase the value of the force P, it will ultimately increase the value of the strain. And this increment in the value of the strain will also increase the value of the stress. So if you plot this relationship, you will get the region of O to A. Initially the strain value is 0, and according to that the stress value is also 0. And as soon as you increase the value of the strain within the elastic limit, according to Hooke's law, the material will give the relationship between the stress and strain as a sigma proportional to epsilon. And that's why, as you can see, that particular relationship up to the point A from point O. So OA is the region within which the elastic limit holds good and Hooke's law is perfectly applicable. Now, if you remove the load from the specimen, the material is perfectly within the elastic limit, and that's why, due to this unloading, the material will try to regain its original position or original condition. So that's why this is the perfectly elastic deformation, and Hooke's law is perfectly applicable within the O to A region. Now, if you further increase the loading, it will increase the strain value, and now from A to B point, you will not get the proportional limit, or you will not get the straight line as it is shown in the diagram. So this line is not a straight, it is nothing but the curvature from A to B, and due to this curvature, you will get the Hooke's law inapplicable or deviating in this particular zone. Although up to the B point, the material is having the elastic deformation only, and the material is having the elastic limit only, but up to the B point, from A to B, the material will not hold the proportionality of the Hooke's law very well applicable in this particular region. And that's why the point A was our proportional limit point, but point B is our yield point. Now there is a two different points available in the yield under the yield point zone. That is the upper yield point and lower yield point. First of all, let's explain the point B, that is the upper yield point. Up to B point, I have already told you that the up to B point that the material holds its elastic region or elastic limit holds good up to the B point. Now what happens that whatever forces that you are applying within the elastic limit, that strain energy will be stored in the body, and at the time of unloading, the body will try to regain its original position, and that's why up to the B point, the overall energy which was stored in the body will try to regain its original condition, and that's why this energy is known as a resilience. This is another definition which will be discussed in the upcoming lectures of the fundamentals of machine design, and it is related to this diagram, and that's why you will have to understand this diagram very clearly. Okay, now what happens? Now if you increase the loading, the strain value will increase, and from B point to C point, the material will transform its elastic properties into the plastic properties. So the elastic properties are changing its nature from elastic to plastic, and that's why the material will face a little bit drop in the stresses. As you can see in the diagram, from the B point to C point, the stress value are declining, and at the C point you will get the important point which is known as a lower yield point, where the material in the between the B to C point, the material is changing its property, and that's why the combination of elastic and plastic properties will be achieved within this zone. And that's why we don't want to keep our material in this particular zone, because in this zone the material cannot be determined for the particular failure, whether it is a plastic failure or a elastic failure. And that's why the lower yield point and upper yield point zone is undefined zone, where you cannot determine whether it is a plastic zone or elastic zone. Now at the point C or a lower yield point, the material will start gaining the strain hardening. So this is a process where the material will be hardened, and that's why its toughness will be increased. Now whenever the material gets hardened, you will require more stress to deform it a little bit further. So whenever you increase the forces from the point C, you will see there is an increment in the stresses that are available from the point C. And as you can see, the material will demand more amount of a strain to gain that particular stresses from the point C. And that's why, due to the strain hardening, we can see in the diagram that you will achieve the point D, which is nothing but the ultimate point. Now at this particular point, you will get the maximum amount of the stress the material can carry, or we can say that the material can absorb maximum amount of the strain up to this point. After this point or the point D or ultimate point, the material cannot withstand the more amount of a strain that you are applying on the material during the working condition. So this is the maximum level, or this is the maximum energy the material can carry or material can absorb, and that's why we named that particular point as an ultimate point. This is the point D, ultimate point, and where you will find out the accordingly maximum amount of the stress, that is known as the ultimate stress, and up to this point you will get the maximum amount of energy to be carried by the material. Now at this particular point, the necking of the material will be started. Now due to the necking, the cross section area will be reduced. Due to the reduction in the cross section area, our basic formula of the stress is nothing but the force upon area. As the area reduces, and the material will be weaker from the point D, and that's why we can say that the material will demand less amount of stress to deform further. So if you increase the value of the strain, you will see that there is a decline in the stress value, and from the point D to E, the stress value will be gradually decreased. Now at the point D, we have seen the necking of the material, or we can say that there is a first cracking of the material, and the material will be weaker. From the point D to E, this weakness will increase or improve and ultimately last at the point E. You will see the fracture of the material, or we can say that the material will be failed at the point E, which is nothing but our fracture point. So this was the whole diagram of the stress strain diagram, which we have plotted from starting the zero force value or the strain value to the failure point value. Okay, and from plotting this kind of a diagram for a different material, you will find different properties of the material, and from that particular different properties, you can select the material that is suitable for your working condition. So this was the basic idea of the stress strain diagram. Again, there is another important point which can be identified from this particular diagram. That is nothing but the difference between the brittle material and the ductile material. We all know that the ductile material are those material which can be easily elongated or can be deformed easily. Okay, and whenever you apply the forces on the ductile material, you will easily identify the yield point zone and the upper yield point and the lower yield point zone. Because in the ductile material, it can be easily identified the elastic zone and the plastic zone. But in the brittle material, the elastic zone and plastic zone cannot be easily identified, or the stress strain diagram of the brittle material doesn't differentiate the yield points in the different yield points differently as we have identified for the ductile material. So the brittle material will directly reach up to the ultimate point, and from that ultimate point it will fail drastically, and that's why we cannot identify a yield point zone in the brittle material, and that's why the maximum amount of the stress that is permissible for the brittle material is ultimate stress. And for the ductile material, we can identify the yield point in the diagram, and that's why the maximum permissible stress that is allowed in the material for the ductile material is yield point stress. Because we can say that in the yield after the yield point, there will be the necking of the or there will be the deformation of the ductile material which will start from the point C, or strain hardening will start, and it will fail the material drastically, and that's why we cannot allow material to go beyond the yield point for the ductile material. So these are the basic points which you have to keep in mind while selecting the ductile or brittle materials in the upcoming working conditions. So based on these points, we will be defining different another parameters like the factor of safeties and different properties like the toughness, resilience, proof resilience, and for those particular property you will need this kind of a diagram. Okay, till then, thank you.